approximate these zeros by using Newton's method. Just a reminder of that method. If we have a function, then we want that's a bad drawing.
That's a bad one.
We would like to have a zero there.
I have a question. Why every class is in this way?
It's not. Every
Except
class.
for every class, it is. Come on. Almost adult person.
I'm not.
How old are you?
17.
Well,
18 is?
Yes, an adult. But I'm not
It only
almost there.
takes
It's quite a
one to
while
wind
away. Like a woman.
It's only like
Man, what? Watch out.
Okay. So if we were to take a guess and then draw a tangent line from that on the graph at that point, use that as our guess of the zero, our next guess.
That was a terrible guess.
It was pretty bad, but this one's better, and the next one will be better, and so on. So just a reminder of how we get that. If we want this point, this value of x, it's part of this line, okay? And this line has a couple of points here. This would be the actual zero, but this is the guess that we're wanting to get. So this is like x sub n plus 1, and of course the y value at that point would be 0. This guy here would be x sub n, the guess before x sub n plus 1, f of x sub n. And we said that the equation for a line is y minus y1 equals the slope times x minus x1. The y we're trying to find, or no, the x we're trying to find is this guy right here. We can call this x sub n, this is x sub n plus 1. So this would be y sub n, this would be y sub n plus 1. And the y sub n plus 1 is the one that goes with x sub n plus 1. It's just 0. 0 minus y sub n, or now we can call this f of x sub n, equals m, which is the slope, which is the derivative. The derivative at x sub n times x sub n plus 1 minus x sub n. And this is the guy we want to find. So first we'll divide by f prime. Divide by f prime of x sub n. Then we'll have x sub n plus 1 minus x sub n. So we'll add x sub n to both sides. So we get x sub n, that minus sign, so it's a little here. Minus that. That gives us our next guess every time. So this is the number of our guess, n. And this is the x that we're talking about. This is the y value at that x. This is the value of the derivative at that x. And then we take x of n minus f of x of n over f prime of x of n. Okay. And this would be the next guess. So our first guess should be something close to the cube root of 1/2, just by our intuition. 1? What about a half? I think that's okay, we'll do 1. 1. And what's f of 1? And here's f. So what's f of 1? Negative 1. 1 minus 2 times 1 would be negative 1. Okay, well, apparently we need f prime, so let's find f prime.
Negative
6x squared. So what's the value of f prime at 1? 6. So if we take 1 minus negative 1 over negative 6, it's 1 minus 1/6. 5/6. So that's our second guess, 5/6. And now it might be helpful to just grab the old calculator and calculate these things quickly. So f is 1 minus 2 times x cubed. So 1 minus 2 times x, which is 5/6 cubed. So negative 0.1574.
That's what I got.
What did I do wrong?
Oh,
Oh, wait.
oh yeah, keep going.
Yeah.
Never mind. I thought you did the whole thing, but you didn't.
Nope, I did f,
Right.
then f prime. F prime is negative 6 times x, which is 5/6 squared. Negative 4.16667. Okay. And now we'll take 5/6. 5/6 minus a negative 0.1574 over negative 4.7956. That's the next guess. That's the third guess. Do it all over again. Keep doing it until we get better at our guesses. So it's x, f of x will be 1 minus 2 times 0.7956 to the third. That's negative 0.0072. Then we need f prime of x. It's negative 6 times 0.7956 squared. Negative 3.7979. Okay. 0.7956 minus negative 0.0072 over negative 3.7979. What's 7937? That's our next guess. How close do we want to be?
That's quite close.
Is it? Okay, how close does the book want us to be? 0.001. We're not quite there, right? The difference between these two is more than 0.001. It's somewhere around 0.002. So probably one more to do it for us. That'll be all. So we need f. F is going to be, well, let me go back to the last time I entered f. There it is. And I'll just replace this with 0.7937. 0.7937. Oh, wow. What does that mean?
That means that you take the decimal and move it to the left 6 places.
6 places. Is that good?
Yeah,
good that it's that
really,
small?
really close.
What do we want this to be?
0.
0, right? We want f of x to be 0 because that's what we're looking for. A 0 of the function. So it's good that it's this small. So 5 zeros, then 1, let's say 2. 1, 2, 3, 4, 5, and 2.
That is so close.
Okay, then f prime. I'll bring back up the last time I did f prime. Not that. That's it. 0.7937. 0.7937 minus not a negative
I'll just stick to humble pie Fridays.
Okay.
Higher one like that.
So this is square root of x plus 4. This is 2x plus 1.
Yeah.
We want to find the intersection, but the Newton's method is not for finding intersections, right? It's for finding what? Zeros. How can we turn these two functions
Into one function.
into maybe one function that has a 0?
Yeah, that's what
So if you subtract them.
we want.
Subtract 1
We want
from
h
the
of
other.
x.
Yeah.
H of x is equal to 2x plus 1 minus the square root of x plus 4.
Yeah.
Okay? Where these intersect,
Bang.
the y values are
The same.
the same. So if I subtract the same from the same,
0.
it's 0. Okay? So if this is 2x plus 1 is that, and we're going to subtract the square root. So here, we'll get positive values, right? Because 2x plus 1 is bigger than the square root of x plus 4.
Yeah.
So this will be about that much. Okay. At this point, it'll be about this much. Okay, so something like that. And here it's going to be pretty small. It'll be about that big. Here it'll be 0. And here, this one's bigger than that one. So when we take this and we subtract that, we'll get negative values. So we'll have a negative about that much, negative about that much, about, let's see, right there, that much. Okay. So if we look at the new function, it looks like something like that. But we're looking for that 0. That's all we care about. And we know what we're going to do each time is find h of, actually first we need to know what x is. We need to know x of n, and h of x of n, and h prime of x of n, and x of n minus h of x of n over h prime of x of n. So we need h prime. What's that? 2 minus
1/2 times x plus 4 to the negative.
Boom.
Differentials. So let's do this a little faster. Instead of entering h of x and h prime of x every time, I know that this is going to be something I do over and over and over, repeated iterations of this thing. So let's put that in the calculator just the way it looks. Some number is going to be plugged in for x, and then some number is going to get plugged into h of x, and there's h of x, and that's going to be the numerator of my fraction. So we'll have 2 times x, plus 1, minus the square root of x plus 4. Who is eating an orange?
What?
Well, at least it's not cats. That's a relief. Over h prime. H prime is that guy there. That's going to be the denominator. 2 minus 0.5 times the, we could just say times the square root. No, times, not the square root. Times, because it's a negative 1/2. X plus 4 to the negative 0.5.
Oh, come on.
Negative 0.5.
That is impressive.
Okay.
You can do that.
So now I just need to tell the calculator what x is. Just go ahead and hit enter. Now that's dependent on whatever x is right now. I don't know what that x was. What x should I use as a first? Like as my seed.
We should do 1.
1,
Let's do 1.
2. We're gonna do 2. 2. Who said 2? It sounds more cocky. Okay, so it'll sound a little more cocky saying 2 than Derek did 1. So we need to take 2 and we need to store it as x. Now x is 2 and we can bring back this guy here, and now this will calculate it as if x were 2. That's our first guess.
Toy.
We're gonna get there, don't worry. Right? So then, now I want this to be x, right? Right? So that's easy. I'll store that as done, and I'll have to bring this guy back up.
Wait, how do you get it to say?
You just press store and it automatically knows that you want the answer to be.
Oh.
See how, if I don't do anything, before I press store, when I press store it automatically puts answer. It assumes that I want to take this and store it as x, which I did want to do. And I can hit enter again with that new x. Okay, and then I can store this as x. But see, all I'm doing is taking the output of this, and the next step is always to store that as the new x. So instead of doing that step every time, we'll have it automatically do that by saying take this number, whatever it is, and just store it as x, and that'll be, that's the very next thing that I want to do.
I have a question.
Yeah.
Okay. So say I put that whole equation in,
Yeah.
and I forgot to do store x.
Yeah.
Is there a way that I can go back up without having to retype the whole thing? Because I can't figure it out.
I've been doing that.
Yeah, but I haven't been able to figure out how you've been doing it.
Which calculator?
Here,
It's
here.
simple. She'll show you.
Can we do the table then?
Look, look.
Sure.
Yes, it does too.
It doesn't.
And if not,
So what this is, if I just press enter without doing anything else, it will automatically go back to the most recent thing I've done, which is to do x minus h of x over h prime of x,
Oh.
and to store that as the new x. So it's just going to keep doing this circular thing. It'll take this, put it in for x, do the calculations, put that, store that as x, come out with a new number, and then it'll put that back in for x and store that as the new x, and so on and so we just get to that's that. Right? We can't get any better than that. Because the decimals have run out.
Why don't they just
So-
go the whole screen?
The whole screen? Oh, I don't know.
Because it has like 6, 5 numbers.
You got me? I'm not a calculator engineer.
That's not a copy. Come on.
I don't care.
Why did you pick a TI-83 to download your computer?
Yeah, seriously.
Why didn't you like a TI-84 plus or like a?
Have you seen the calculator I use?
Like a silver
It's this
edition.
calculator.
Well, doesn't you need to put up there on the board?
And actually, truth be told, this is a TI-84 and a TI-83 skin. It does, not silver.
Yeah, but if it doesn't have block view on it, then
You
it's
say
not
all
the,
of us
it's not the
have
silver edition.
not
It's
that
not
one.
the, it's not an equal.
Anyway,
Oh,
That's
I
the
have
only
that
thing
one.
block needs back. It's basically,
But
point
you're not
six
using it,
five,
right?
or 0.5687.
it's basically useless without block.
Right? Or, as Kendall was mentioning, we can do this in the table, where in y1 and y2 we have h of x and h prime of x, 2x plus 1, and 2 minus 0.5.
Wait, you forgot the
Really?
minus x
What did I use?
minus the square root.
Oh, wow. Minus
Yeah, we're gonna have like 10.
the square root
Think the number.
of x plus 4.
How big?
Think the function.
Yeah, that was. X plus 4
You really are.
to the
They do it for other people. There's one of these numbers that you don't understand, pressing the hand instead of
Okay.
It's basic.
So at each step along the way, we can use the calculator to do these calculations for us. We can also do a third one. That is x minus 2x plus 1, like what we've been interested in the other thing. 2x plus 1 minus the square root. X plus 4 over 2 minus 0.5 times x plus 4 to the negative 0.5. do that. See, that's each part of the table.
See, I didn't know we could enter that third part. That's tricky, Mr. Stewart.
Enter anything you want.
Tricky.
What?
Yeah, I know.
Using vocabulary for fun.
All right, then we go to the table, and the table will give us the actual values. What's going to be our first guess?
One.
2.
2. Oh, that's what we
Oh,
started with.
that's right, because Kendall said it.
So we'll put in 2.
What did you say?
Which means our h of x of n is...
So this is 2.5505. This is 1.7959. And we can move over to the third function. We get 0.5798.
And there they are.
And then enter in that one.
98. So now take 0.5798. Enter. That's our first. This is our second iteration
Look at that.
with 0.5798, which gives us
Oh.
0.01955, 1.7664, and moving over 0.56873.
This is way easier than what I did.
Why did we start with 2?
You have to move over to the right.
No, I know how to do that. How do you like make it show that number?
He entered that part into the white.
You have to have 3 functions.
He entered in.
You
But
do.
he entered
For
in
it to
the
show it.
If there's no function, there's no output.
Boy. So how do you do this? You do that? No, you don't.
Is there a way you could like why?
No. No. I'm
But you
asking
can
you
do
a
what?
question, but I don't want your answer.
Okay, I just know you could put it into the y equals part. I would always just quitting and then going and doing it.
That's the way I showed you in class, but you know, you aren't clever enough, I guess. to do that.
Okay.
That's rude.
That's
I'm sorry, I was
It's
trying to be
cocky.
cocky.
Sorry.
You passed copying. You got to rude.
5, 6, 8, 7,
Well, it's right over
3.
there.
I'm still not sure why I started. I really do.
Started at 2?
Yeah.
Because
Because
Kendall
we
was
picked
cocky.
Two,
Because
yeah.
Kendall was cocky.
She said it.
We just picked 2.
Yeah.
All right, so this is our next guess. 0.56873. And we entered that in.
Yeah, bro.
For the function itself, we get
So totes crazy.
0.03179. We get
Oh my god.
1.7665. You didn't?
Derek.
What? I'm just doing function and stuff.
I got 1.2.
What you doing? Just
You put 0.58.
Thank you, Colby. I know it's stuck in my head.
I did, yeah.
Got it.
56873.
How's that make you feel on top of Friday?
You're just kidding.
Ah.
There it is.
My dad.
You wrote it down, right?
Every time.
Thank you.
Best.
So 0.0000012 and 1.7661.
Oh, I bet this next one's gonna be it.
0.56873. So this is great.
Hold on, what? Can we go over that third equation that you put in? Because I don't understand.
Got x minus. Now I know I'm going to have a numerator, so I put parentheses. 2x plus 1. 2x plus 1 is that thing in the numerator minus the square root of x plus 4. Making sure I have all the parentheses I need around this one for the numerator. This one is the square roots parentheses. So square root and then numerator parentheses divided by h prime of x. Here's h prime of x. Parentheses for the denominator, 2 to minus 0.5 times parentheses, because I know I'm going to raise this x plus 4 to a power. 0.5 times the square root of x plus 4 to that negative 0.5 power. And close parentheses.
Okay.
A source of a problem could be maybe you didn't do negative 0.5, you did negative 1/2. And if you did negative 1/2 and didn't put parentheses around 1/2, then it's only raising it to the negative 1 and then dividing that number by 2, not raising it to the negative 1/2 power. That might be something that happened to you. But just got to make sure that the calculator knows exactly what you want it to do. And that's exactly what I wanted it to do.
Yeah.
I like this way.
Yes?
I didn't get that answer. I'm off by 3, whatever after 1,000.
10 thousandths?
I got 0.584. How did I get that?
584.
That is strange.
15. 5, 6,
Just
8,
put, what is it? And put 1.
5, 6, 8, 7.
No. What did you say?
When were you doing it?
For this reason.
Oh, you started with 1.
Wait,
Is
no.
that really clear?
It's the exact same. It's the exact same.
Yeah.
It's because you don't have enough time to do it. It's having the like.
Not 5 maybe. What did you do? He did this. Like 5 minutes. Yeah. And pissed everyone off.
Not everyone else. I was too upset about it.
Who?
Fine.
No.
We were talking about it. Probably chat. Appreciate it.
What is that? This is the writing one.
Oh. This one was hard.
I thought this one was easy. If you
Kidding.
use a diagram-
25 is exactly what Kirsten got extra credit for doing. It's describing Newton's method using that sketch. So, let's see, what did it say? In words or using a sketch? Oh, and using a sketch. So, what we need to do is, since it's Newton's method is for approximating zeros, we need to sketch a graph with zeros. So here's one.
That's lovely.
Okay, and we use Newton's method to approximate zeros. There's a 0. We could do this one, but we'll just choose to do that one. We do that by using the derivative at some point, x of n. So that point is there. So this is our initial guess. And this is the tangent line of f of x at x sub n. This right here is the x-intercept of f prime of x sub n. I shouldn't say it that way. I should say of that tangent line at x equals x sub n. And that's, and then we do the process over again.
Iterations.
Iterations. So we can say with the initial guess of x sub n, we find the equation of the tangent line at x sub n and its x-intercept. This x-intercept is our when will Newton's method fail?
When
Good
the
guess.
tangent line is a horizontal line.
Okay?
And
If the tangent line is horizontal,
and if it like bounces back and forth.
if the guesses bounce back and forth. Or maybe if f of x sub n is undefined, that would happen. You could say the tangent line is horizontal or
Cusp.
or the slope is undefined,
I.e. a cusp.
i.e. a cusp or a hole or a glass tote.
This whole obsession with cusps. This is the best word, you know?
Cusp, it sounds like a gross word.
Okay, let's pass your homework, please.
What? Right? Oh yeah. Yeah.
You know what I appreciate? Ages at like
Oh, we didn't do that. We did that one
as
time.
long as you back and you don't like
After they both walked.
No, I was 7 foot.
No.
I don't like to do that.
And
Just
honestly,
like,
like, it's a shipwreck.
Alright. Okay. Hey! Thank you. Ryan. Thank you. What function is this blue function?
What'd you say?
What function is this blue function?
Oh.
The
Yeah.
sign.
Side.
What's the sign of 0?
Zero.
0. What's the sign of pi over 2?
One.
1. Yes, so yeah, it's the sign. And we can look at the tangent line of this function anywhere we want.
oh, that's cool.
Here, there, over there, whatever, okay.
Can we draw a little car?
No, what we're going to do is we'll look at the tangent line right about there, right at 0. Okay. Let's see if I can zoom in there. So what we're going to pay attention to is where they intersect, right? Where the tangent line is actually the tangent line at that actual point, that point of 0. So what do you notice as I zoom in? What gets real close?
Schooner.
How did that happen? As I zoom in, what's getting really close? Yeah. The original function sine of x and its derivative are they're only exactly equal right at 0. When I start to move away from 0, are they going to be different?
Yes.
Yeah? By how much?
Small amounts.
Very, very small amounts. In fact, I've already tried to do this earlier. And
Oh. Now you've done it.
You went too much there.
and just believe me when I say that I tried to zoom in and even in this window to see the two functions kind of separate to a degree that we can see how far off they are, and you saw this program get messed up before, and it gets messed up before it ever shows how far apart these are. So they're really, really close to each other.
Actually, a better program.
It's the program's fault.
Yeah, it is. It's a computer. They know everything.
Is it your fault too?
No, nobody's fault. It's the current level of technology's fault. Don't have it readily available for people.
So you're complaining about technology.
I'm not complaining at all. Okay, so we're going to use that tangent line to approximate the values of the function close to that point. Right? Whatever point we choose to look at the tangent line and draw a line that's tangent to the curve, we're going to look at that tangent line and use it as an approximation. It's called linear approximation. calculations on a line and find out what the values are on that line than it is to do calculations for perhaps a complicated function. So if we've got a function and we have a line that's tangent to it, let's talk about how we're going to approximate the values that we want to approximate. I'll get a little bit away from this value of x. We want to approximate values of this blue function close to x. A little over here, a little bit over there, using this tangent line. Now to get far away from x, how are those approximations going to be? Way up, right? Way more off than I want them to be. But stay close to x, and those approximations will be very close. So I'll come out here just so we can see all the stuff that I'm going to label. So here's the actual value that I want to approximate. I want to use this red line to approximate the value at this value of x. And we'll just use this label delta x. And so this value of x will be what?
X plus delta
X plus delta x. This guy here will be x plus delta x, comma f of x plus delta x. Agreed? Any questions about that? You got an x value, you're going to find the y values, plug it into the function. This right here will be x comma f of x. And so that would be the actual value, but we want the approximation. So this guy right here, we need, like, we want to find this, let's see, what, I wrote it down earlier, I want to know what actual numbers or labels I used.
Stu, when you were a kid, what was your dream job? Besides math teacher?
It's all over the place.
You're in the wilderness.
So this point we'll call x plus delta x, comma y. Okay, for this function y. Y of x. So remember that the point slope form of the equation is y minus y1 equals m times x minus x1. Okay. This would be the y that we are looking for. This approximated value right here, this y value. So that y value minus y1, which is just this guy here. This point is on the tangent line. So y1 would be f of x equals the slope at the value of x, or at x plus delta x. It's all the same. So the slope of that line right there times this x, which we'll call x plus delta x, minus x, this original x here. That's x of what? cancel and we get f prime of x times just delta x. 1 minus f of x equals f prime of x times delta x. So f of x plus f prime of x delta x is going to give us this y value. And if, like, let's look at the actual value of f of x, or f of, yeah. So let's look at this value. Let me restate what this is. This essentially is the equation of the tangent line for the tangent line at any x for this blue function. So this y value represents this, well, any y value on the line that I want to calculate. So this y is a y value on the graph. F of x is this value right here at the place that we're actually shooting the tangent line up. So if we look at the value of f of x, the value of the function, the blue thing here, is exactly equal to the y value on the line, because the y value on the line is given by this, or f prime of x times delta x. Why are these exactly the same? What about this expression would tell me, since we're right at x, how do I know these are exactly the same?
F of x is the y value at that spot, and then equation has its y value.
And we can see that they're the same by the picture. Let me ask it this way. What's delta x worth at that point? 0. So how much is this? 0. So they're exactly the same at x. And if I move away, like this far away, if I move very far away, is delta x very big? It's very small. And so for small values of delta x, I'll be adding on a tiny little piece to f of x. Okay, whether that piece be positive or negative, it depends. But I'll be adding on a tiny little piece to f of x, so I'll just be the smallest bit away from the actual value of f of x. Okay. So now you might be wondering, why in the world would we do anything like this? And it's kind of like Newton's method. Newton's method is really cool if you're Isaac Newton and you don't have a TI-83. But if you have a TI-83 and you want to find the square root of 7, you just type in square root of 7 and it tells you to a lot of decimal places and you're happy enough. If you're Isaac Newton, you don't have a calculator and you're really happy to have Newton's method to approximate the zeros of any function you want to make. So you make the zero of the function be the number you want to approximate, and there you have it. You can approximate those zeros with not much trouble. Same thing here. Maybe your function is a really complicated, crazy function. It's hard to actually calculate the values, or it takes a long time. Instead of that, if we want to just, if x has a value that we know for this blue function, or for our original function, we can go from there and approximate values near that x value with just a line. This is much easier to calculate than, say, the cube root of x plus the sine of x cubed over 2 times the tangent of x over 2. You see what I'm saying? If it's a really complicated function, it becomes quite the chore. But if we use the linear approximation, it's much easier to use this line to approximate the value that we want to find. So if we move away from x, then we can say f of x plus delta x this is f of x plus the little bit of change in the y value will give us our approximation. Alright. Now, I know it's not crystal clear right now. But are there any questions that you can ask that I can answer? Or should we just do an example? Okay? So what we're going to use is this. Okay? One more thing before we do an example, it's just a small notation thing. When we're using such small values of delta x, we give it a different notation just to denote it's very, very small. Not just any old delta x, but very small delta x's. So we'll say that f of x plus delta x is approximately equal to f of x plus f prime of x times dx. Okay? It's the same concept as the dx in dy over dx. Very small change in x. A very small change in x is going to give us a very small change in y. Okay? And that very small change in y plus the original y value will give us our approximation. Do an example number 1. So you can see the table. It all kind of centers around the number 2. 2, and then we get a little bit away from 2 and a little bit further away from 2. We're going to look at the actual value of x and the value of the tangent line at x. So what's the value of x of f of x at 2? 4, right? 2 squared is 4. Let's go ahead and fill these in. That's 2.01 squared.
4.04. What?
4.04.
4.
How about 2.1?
4.41.
2 point, what?
4.41.
4.41. Okay. How about 1.99?
3.96.
1.9? 69?
361.
Very good. So, this represents 2 plus delta x. What's delta x here? How much has x changed? 0.01. Right? This is our delta x, our small delta x, our dx. And for this one, we have 2 plus delta x. How much is delta x? 0.1. Here we have 2 plus delta x. What's delta x in this case? Negative 0.01. This is 2 plus a negative 0.1. Right, because we have to think of it as x plus delta x.
What happened to the added line?
On what one? Oh, sorry, plus a negative. What happened to what?
F prime.
We haven't used it yet. Remember that I said we're going to use this. That the value of f a little bit away from x is going to be approximately the same as f of x plus f prime of x times dx. So we're going to use this to approximate the values. We found the actual values just a moment ago, and now we're going to find the approximations and see how close they are. So f of x plus delta x is equal to f of x plus f right at 2. Right? Because the tangent line is touching the graph at 2. That's kind of the idea. So they're going to have the exact same value. But as we move away, this first value, we'll use this one. We have f of 2 plus 0.01. So 0.01 is our delta x. That's equal to f of x. What's f of x? It's what? 4, right? Because x is now 2, so f of x would be f of 2, so that'd be 4. Plus f prime of x, so we should find f prime of x. F of x is 2x.
4.
It's, yeah, it would be 2 times 2, which would be 4 times dx. What's dx? 0.01. Maybe you can see now, like, why it's important to have plus your delta x. Always plus delta x, including the delta x is a negative.
Why is that 4? The first one.
Yeah.
This one?
Yeah.
Okay, so we're going to, here's x squared, and let's say that's 2, and there is, what, how big is that? 4, right? Because x squared is 4, and then we've got this tangent line coming off of there, and we're going to use this tangent line to approximate the values near 2. So x is 2. Our home base, I guess, so that our center of all of this is x. Did that help? Okay. So x is this constant thing. We could, I guess for this specific example, we could say this is always going to be 2. We're going to add a little bit of a difference and see what our approximation, I should put approximation to us. So we should have approximately 4 plus 4 times 0.01, so that's 0.04. So what do we get for our approximation to 2 decimal places? 4.04. So if all we care about is 2 decimal places, apparently for dx or delta x of 0.01, the tangent line is close enough. Do it again for, what's going to be our next delta x we're going to use? 0.1. Doesn't have to be 0.1, we can do negative 0.01, negative 0.1, but seems natural. We'll move on to 0.1. That's going to be approximately f of 2 plus f prime of 2 times what? What's dx? 0.1. So approximately, well, f of 2 is always 4. You see what we're doing here? We're going to take 4 and always add on this little bit of the y value from the tangent line. So always 4 plus, this is going to be always 4 times 0.1. So 4 plus 0.4, so we get 4.4. Okay, so now we can start to see how we're a little bit off. We have 4.40, where we know the actual value is 4.41. That makes sense. The further away we get from the x value of 2, we're going to get a worse and worse approximation. If we let the delta x be like 2, if we move 2 away, that's going to be really way off. That's why we don't let it go very far away. We want dx to be a very small number. Do 2 plus, what's a new delta x we can work with? Negative 0.01. So, you notice how this and this keep being the same thing? Right? Because f of x is going to, f of 2 is going to be a constant. 2, and f prime of 2 is going to be a constant. F of 2 is 4. F prime of 2 is also 4. And we're going to multiply that by dx, which is negative 0.01. That's 4 minus 0.04. That gives us 3.96. Accurate to 2 decimal places at least. we get 4 plus 4 times dx, negative 0.01. Sorry, negative 0.1. That's 4 minus 0.4. 4 minus 0.4 is going to be 3.60 exactly. And again, we're off by 0.01. So if you don't care too much, if you're okay with being off by 1/100th, then the approximation is good enough. The further away we move from x, the more and more inaccurate our approximation is going to be. Do number 3. I'll be around to help here. Right. Number 3.
Number 3.
Yeah.
And we also know we're going to need f prime. It's 5x to the 4th. We know that we are going to approximate the value of the function, this function, a little bit away from x. Just a little bit off of x and approximate that value, and that's going to be approximately the same as taking the tangent line and and finding its y value at that point. And its y value can be found with f of x. That's your original y value, right? That's your baseline. You're starting there at that y value, and then you're going to add a little bit. Okay? A little bit. F prime of x times the change in x. Let's think about that. Here's a tangent line. Here is that f of x, and this is x. Okay? That's where it's tangent to the curve. We don't really want to look at the curve. We just want to think about the tangent line. Okay? So to get this y value, we could say f of x plus this little bit of a difference in y. Right? This thing is dx, a little change in x. This thing is what we call dy. Right? If this is dx, this would be dy. That's the change in x, the tiny little change in x. That's the tiny little change in y. Okay. So dy can be found if you think about this slope of this line. Think if dx were a full value of 1. Then the change in y would just be, see the slope is dy over dx. Okay. Then dy over dx equals f prime of x. Right? Does that make sense? Dy dx equals f prime of x.
Yeah.
Dy over dx. So dy could equal f prime of x times dx. See, that's what we get. That little change in y can be calculated by taking dx, that little bit of a change in x, and multiplying it by the slope of this line. Okay. If this is the slope, it's rise over run, right? And if the run were 1, then the rise would be just like the full value of the slope. It would be dy over dx. It would be f prime of x. But we're not going to go that full rise. We're just going to go a fraction of that. We're going to go that much of the rise times that little piece. Does that make sense? This dx is not 1. It's very small. It's not 1. It's very small. But let's do number 3, and we'll use the actual values, and I think it'll make more sense in that context. So let's section that off and do our work over here. I'm going to be filling in this table. This is x, and this is f of x, and this is not f prime of x, but the value of the tangent line. The line is tangent to the function at x. So what's our x value? 2, and then we're going to move away from 2 by small increments. First we're going to want to find f of 2 plus one of those delta x's. This point what? Negative 0.1 plus negative 0.1. That's that first one, right? So we'll just go from left to right. So that's going to be approximately equal to f of x. So what's f of x? It's 32, because 2 to the 5th is 32. And for that matter, what's the value of the tangent line at 2? Also 32. Okay. Remember, this curve looks probably something like this, and the tangent line at 2 is going to be touching the function, and so their y values are going to be exactly the same at 2. And since we're here, let's fill in these values. So what's f of 2.01? 2.01 to the 5th?
Yes.
32.808.
And 2.1 to the 5th?
40.84.
40.84. 1. You plug them into f of x. F of x is x to the 5th. So 1.99 to the 5th.
31.208.
And 1.9?
24.7.
Point what?
76.
76.
6.1. So this is going to be f of x. What's f of x? 32. Now this is where you might be confused. This is plus f prime of x. F prime is the derivative. The derivative tells us about what? What information does it tell us about the original graph?
Slope.
The slope, right? F prime at that value is the slope. So in the previous example, you may have gotten mixed up and thought, oh, this is 4, so this 4 goes down. F prime. So what's f prime at 2? 80. That's really steep, isn't it? And it should be steep. This is going to be very steep. X to the 5th is very steep at 2. It's getting big very fast. Okay? So this is a slope of 80. That's going to really climb, right? It's going to be kind of a big difference, even if you move over 1. If you move over 1, then how much is your delta y? How much have you changed in the y direction? 80, right? It's rise over run. That's what this is. So if you move over 1 in the x direction, that's your run, then your rise is going to be 80. So if you just go from 2 to 3, you're going to go from 32 up to 112. Right? So we're getting going there. But we're not going to go all the way. 1 is a huge dx. That's a big change in x. We want really small changes in x. So we're not going to go a full 80. We're going to go a fraction of that 80. How much of that 80 are we going to go? We're going to go negative 0.1 of that 80. Okay, so that's what I was trying to say over here. It sounded confusing. We're not going to go that full 80. We're going to go a fraction of that. That's why we let dx be really small so that we don't go so far. Okay? So we can calculate this value as 32 minus 0.8. So for this value we get 32 minus
Isn't it
0.8.
1?
What?
Isn't it 1 over 1?
Oh, this one.
Yeah.
So we should get,
No.
So that would be 8.
But you
Yeah.
plugged in
You
point.
did negative 0.1, it should be 8.
Yeah.
negative 8.
Right.
Oh, yes.
60.
You calculated wrong. Alright, so what value do we get then?
24.
24.
24. 24. Exactly 24. So that's a little bit off.
That's pretty off.
It's off by 761 ten thousandths.
It's like 3/4 of it.
Or thousandths, 761 thousandths. So yeah, that's kind of off. But we'll be 1. That's going to be close to, well, this is still going to be 32. This tangent line is still going to have a slope of 80, but then we're going to multiply it by negative 0.01. We're going to go an even smaller fraction of that slope of 80. 2 minus 0.8, right? That's 31. 0.2 exactly. And so now we're only off by 8 thousandths. That's considerably better. Now we'll do f of 2 plus 0.01. 32 plus 80 times 0.01. 32 plus 0.8. 32.8. F of 2 plus 0.1, that's a bigger delta x. It's going to be 32 plus 80 times 0.1. 32 plus 8. So now we're off by 841 thousandths.
Which means our slope is changing a little bit. It's not.
Our slope isn't changing.
No, I mean like on that line, it must be a little bit steeper or a little less steep than it is on the other side, isn't it?
Yes, but what are you talking about? What's more steep and what's less steep?
The original, the curve.
Yeah, the curve, not the line, because the line is straight. Yeah. So the original curve, yeah, that's an excellent observation. That the function is going to be more curved on this side of 2 than it is over here. That's exactly what it looks like, right? It looks kind of like a cubic. It does that kind of a thing. It comes out like this, like 1 to the 5th is 1, but 2 to the 5th, huge jump up to 32. 3 to the 5th is 4 times 3. Like 200 and... Yes, exactly. 243, that's a huge jump, and an even huger jump. And every time you make each successive move over 1, you're getting steeper and steeper. So that's an excellent observation. All right. So any questions about that? About that particular exercise? Now, let's take a look at this guy right here. This is our approximation of how much y has changed. It's not actually how much y has changed on the original function, but it's an approximation. It's close. The actual change in y, let's say the actual change in y will be from here to there, the actual value of the function. This would be delta y. This, I already have it labeled over here, but this is dy. Okay. Well, delta y, how do you actually calculate delta y? Change in y, how much difference there is between one y value and the other. If I have a function, and here's a point, and here's a point, and I tell you that this is, let's just use those same labels, x and f of x, and x plus delta x, and f of x plus delta x. How do you calculate how much distance there is between, vertical distance between this point and this point? No. Just subtract one value from another. That gives you a difference. That's exactly what the difference is. So delta y is equal to f of x plus delta x minus f of x. You take this value up there, subtract this y value here, and you'll have just the distance between the two. The difference between those two values. We can approximate that value if we have a tangent line. If we have a tangent line, then that's a much less complicated issue.
You have to find delta, or you have to find d of x and delta x before you find x.
You have to know what delta x is, yeah. You need to know what dx is. So we can approximate this delta y thing, call it dy, and we'll say that it's equal to of x times our tiny, tiny, tiny change in x, dx. And we can see even just by this picture that delta y, as long as dx is very small, which is, it is very small, that's why we write a little d like that, signifies that, it's very close to f prime of x dx. Who's confused?
Well, I know there's. How do you get from the delta? Is dy and delta y the same thing?
No, they are close to the same thing. Because this is dy, right? This is dy right here.
Oh, okay.
So dy and delta y are very close to the same thing. And the closer we get to the original point, the closer dy and delta y are to each other. So delta y, this calculation, which can be really quite cumbersome, is pretty accurately approximated by just take the slope of the line and multiply it by the distance that you traveled away from x. A couple more minutes left, so let's.
Seven, I'm stuck on seven, because I found f of x plus delta x, but I can't,
Delta y?
yeah.
Okay, so let's work on that. I'm gonna cruise through this guy. X cubed. X is 2. And delta x, which is gonna be dx, is 0.1. 0.1. We have this function, 1/2 x cubed, so it's gonna be kind of the squattier version of x cubed. And we're at x equals 2. And we're going to use the tangent line at 2 to approximate the change in y. So the actual change in y will be from here to here, say, for some delta x. And our dy is going to be from here to there. So they're off by some amount, some small amount. So to find actual delta y, we're going to take this y value and subtract this y value. I guess I should have started here, not down the x-axis. And subtract this y value. Is that the bell?
Yeah.
Okay. Well, have a good weekend.
You too.
So does that mean we do
Don't be
all
too
of them?
cocky.
Or what about those ones? You want us to do all of them in homework?
Yeah. Give it a try. I'm going to keep explaining this as you leave, and then it'll be up.
I know. It doesn't feel like it's an actual college Friday.
I think I'm going to
Like,
do
is
that.
this really
You guys have to be
college Friday or
quiet.
is it not?
Where is it?
Be quiet, and I'm going to keep explaining this. But pack up and leave. Get
Where
back
am I
to
keys,
the
dude?
Okay? So the actual change in y is going to be this y value minus this y value, bottom left drawer of my desk. Okay? So for a change in x is 0.01, then x plus delta x is going to be 2.01. So y equals 1/2 times 2.01 cubed. And this other y value is going to be 1/2 times 2 cubed. So we're going to subtract these two values. Cube minus 1/2 times 2 cubed. That's going to be delta x, or not delta x, delta y. But dy will just be equal to f prime of 2 times 0.01. So find f prime, and then find f prime of 2, and f prime of 2 times 0.01. Will give you dy.